All right, let's talk about two curves. If you remember Calc 1, the area under a curve, this should be for you. Formula, see if you can figure out the formula. So let's call this low, and then another function, since it's the area between two curves, another function, and we'll call one O, and then we'll need some bound of this A, the formula for it. It represents the area bounded. When it's my face. Okay, so remember that area under curve is given by an integral, right? So if I want the area, let's see, if I want the area under f, that would be from A to B, it would be this, right? So write a representation using calculus to represent that purple area. Well, it would be from A to B, f of x dx. Okay, well, if I want to find this region, let's use pink. How can I do that? Well, you're probably guessing that I know what the area, I need to get rid of like this area, right? So I have the area under F all the way to the x-axis, but if I subtract from that the area under G, then it'll just give me that pink area. It's that simple. It's just a difference of the two, right? Because the area, this represents the area under F, this represents the area under G. If you subtract the area under G from the area under F, you get the area between the two curves, right? So we can write this as, we know our properties of integration allow us to write this as a single integral, and I am done. That's the formulation for area between two curves. Okay, so if you can find the area under a curve, or if you can do a direct integral, definite integral, then you can do the area between two curves because it's just the difference of two functions, but it's still a definite integral. Okay, you just have to, what do you need to know? You have to need to know which one's greater, right? Because what happens if you weren't given the graph, maybe? What happens if you mixed them up and you did this? You said G minus F. What's going to happen there? Well, it's going to be a negative value, right? Because you're subtracting, like F is a larger area, so you're subtracting a larger area from a smaller area. But this is actually, if you did this, they'd be the same, right? One would be the absolute value of the other. But I wouldn't mess with that, right? Just try and figure out which one's on top, which one's greater, and then you don't have to worry about that, okay? So let's look at an example. So the question here would be, find the region. So here's a typical question. Find the area of the region bounded by x squared and y equals 2x minus x squared. So if you didn't have the graph, there's the graph. But let's say you didn't have the graph. You might have to graph it yourself or just think about it. I mean, I always say this, and you'll hear me say this all the time this semester, just knowing algebra gets you a long way in calculus. I can picture that. I've done that so many times, I can picture that in my head. Y equals x squared, parabola at the origin, right? I can sketch that real quick. I'm like, oh, y equals x squared, that's an easy one. Uh-oh. Where did I go? Okay, we're back. That's an easy one. Y equals x squared centered at the origin. That's your basic parabola. 2x minus x squared I might have to think about, but I would say, well, I could real quickly think, what are the two intercepts? That always helps. To factor out an x, factor out an x, that's the common factor, and you get 2 minus x. And then you can see one is here, and one is here at x equals 2. And this opens down because your x squared term's negative, so you come up with like a kind of a quick sketch of that, and you say, okay, that's the region in question, if it's not given. All right, so then you would say, okay, it's clear to me that this guy is on top. It's the greater valued function. So I'm not sure what my bounds are yet, so I say 2x minus x squared, and I'm going to subtract the lower function, which is the x squared function, And now the only thing I don't have is the bounds. I know it looks like it's 0. I'm not sure where they intersect here. Where is that? In order to find the intersection point, if you're not given the graph, you can find it this way. We do some algebra. All right, you say, when do those two functions equal one another? When do the function values equal one another? What x value? And the bounds are in x, right? So I could solve this real quickly by adding x squared. So 2x squared, subtract the 2x, minus 2x equals 0. And I factor out a 2x, and that, of course, is x minus 1. And with some quick algebra, I realize that this is the point x equals 1. Bad graph. All right, so the area is given by that. Okay, good. Now we get to practice our integration. We haven't done that yet. So let's do that. So now I have my, and then sometimes maybe on the homework, or like let's say I give you let's say I just want to test your knowledge on the idea or the concept of integration between, or area between curves. I might just ask you to set up the area and not integrate it, right? So I say we're going to do a lot of integration coming up, so maybe I'll just ask you to set it up. But let's review our integration, because we are going to need to do a lot of integration this semester. If you look at chapter 8, it's all integration. So we'll do we'll review everything we did in Calc 1, which is kind of what I'm doing now, and then we'll do these new integration techniques, okay? So what do I do with this guy? Well, I'm going to integrate from 0 to 1. Let's simplify this. Is x squared minus x squared 0? No, because it's negative x squared minus x squared. So it's 2x minus 2x squared dx. So I integrate. Whoops. If I integrate, I don't need that anymore. So I integrate, and that's x squared will give me, that's the antiderivative of 2x, and this one would be x cubed over 3, bring the 2 along. And then what do? We do this, 0 to 1. And then I say, well, let's plug in my bounds. So I say 1 minus 2/3. And then I would say minus, and then I plug the 0 into both of these, but we know that if I plug in 0 to that, then I'm just going to get 0. So I don't actually have to worry about that lower bound. Sometimes you do. All right, you don't always get 0. So if I were, just for habit, if you want, you could be like 0 minus 0 cubed over 3 or something like that. But that's 0, so you can leave that out. And then it's just 1 minus 2/3, which is 1/3. Which is still pretty amazing. If you go back to Calc 1, I would always say this. We can find the exact area of this weird looking region. And not only that, I can do it pretty easily. And not only that, it comes out as a nice rational number like 1/3. Okay? All right, let's do a couple more. We gotta do some trig. So this is a good one. Find the area bounded by these two functions on the interval 0 pi over 2. Oh, that's interesting, because look what happens in this case. On 0 pi over 2, it switches, right? The greater guy switches. So what I want to do is add this region to this region. Okay, so if I'm given the graph, I might say, well, I'm pretty sure that's pi over 4, right? And I think, I guess it's a pretty safe assumption, but we're Calc 2 students, so we want to back that up, all right? We want to verify that that's pi over 4. So let's solve this equation. How do you solve this? Well, divide. So we're kind of a weird one. I get sine x over cosine x, which is tangent x. Cosine divided by itself is 1, and then I'm pretty happy that x is pi over 4, okay? So I got to break this guy up, see if this makes sense. If I want to break this up into two integrals, one ends at pi over 4, so I'm going to go from 0 to pi over 4, then pi over 4 to pi over 2, okay? 0 to pi over 4. 0 to pi over 4. And then the cosine curve is on top, right? Cosine 0 is 1. So cosine x minus sine x dx. And then add that to, right? The subtraction comes from the formula for the area between two curves. But I'm just literally adding two areas together, so that's what I'm adding. And then I go from pi over 4 to pi over 2. And the sine curve is now on top. So sine minus cosine. And you might also recognize this. Those to me look like they're symmetric, and I think that's a safe assumption. But like we backed up the pi over 4 thing, we might have to back that up, and it might just be easier to knock it out without doing that. I mean, I'd probably be okay if you assumed it's just 2. If you multiply either of these, we should get the same answer for either of these, right? I can kind of tell the symmetry going on there. If I wanted to do that, I'd have to use like the concept of even odd functions, but I don't know if I want to do that, and I don't know if I want to make assumptions, so I'm going to do it this way. Okay, so I might say area equals that. Okay, so let's finish this one off. The antiderivative of the cosine is the sine. The antiderivative of the sine is the negative cosine. The antiderivative of sine is negative cosine. The antiderivative of cosine is sine, so the negative comes along, and I'm going from, pi over 4 to pi over 2. So my answer then is sine of pi over 4 plus cosine pi over 4 minus sine of 0. This is the fundamental theorem of calculus. Minus sine of 0 plus cosine of 0. All right, that's that piece. And let's see, I'll use a different color, try and organize myself. Come on. That doesn't like that. Let me try this way. Come on. How about blue? And then this one will be plus. I'm going to factor the negative out. And then I say, and then everything's positive. Cosine pi over 4. Sorry, cosine pi over 2 plus sine pi over 2 minus cosine pi over 4. I'm running out of room here. Let me try and squeeze all this in here. That would be plug in pi over 2, and I factored out the negative, so that's cosine plus sine. So I plugged in pi over 2, and then I say minus from fundamental theorem of calculus, and then I plug in pi over 4, so that would be plus sine pi over 4. Sorry, that's a little messy. Let me rewrite that. So in the purple, I got sine pi over 4 plus cosine pi over 4. This one turned out to be a little more complex than it looked. So let's be organized. Minus, and this is a case where I can't just plug in, I can't just assume 0. Plugging in 0 yields 0 because cosine of 0 is 1. Okay, so that's my first integral. And then I say plus the second integral, where I factored out a negative, so I guess we could put a minus in there. But that's the cosine of pi over 2 plus sine pi over 2 minus, from the fundamental theorem, cosine pi over 4 plus sine pi over 4. And that looks, well, a little bit better. It's kind of messy, but looks a little bit better. Okay, so here we go. Sine of pi over 4, root 2 over 2. Cosine pi over 4, root 2 over 2. Oh, good practice. Minus sine 0, 0. Cosine 0, 1. This is just 1 minus. Cosine pi over 2, 0. Sine of pi over 2, 1. What a great problem for a review. Minus cosine pi over 4, root 2 over 2. Sine of pi over 4, root 2 over 2. And then we get some stuff to cancel out. Let's see. This looks like we're going to have 2. And this is where you can see the symmetric part. When I distribute the negative, I'm going to have, well, let's just do it. Root 2 over 2 plus root 2 over 2 is 2 root 2 over 2, or root 2. So that is my integral. So root 2 minus 1 should be this. If I did everything right, it should just be that piece. Okay. and then we're adding it to the other one, which ended up, the algebra gave us a negative, but we'll see, hopefully, that it's the same.